Well, good morning. Thank you for giving us the opportunity to give a webinar about vibrations. Today I will be presenting the webinar, and during this webinar we would like to touch on some topics. We have made an agenda. We will just start with a small introduction, touch on the basics of the vibrations, protection versus monitoring. We'll look at causes and effects of vibrations, condition monitoring strategies, the hardware, some common mistakes, which we see a lot happening in the industry. And we also have presented two cases studies. So a quick introduction. My name is Sietse Drost. I started working in the gas turbine business more than 17 years ago. I started as a gas turbine technician, and along the years I fulfilled different roles, mainly on gas turbine testing, reliability, and diagnostics. And last year I made a decision to fully focus on the condition monitoring, and I got the opportunity to join ISTEC. So that's now my current role as a rotating engineer. And in our daily job, we come across a lot of gas and steam turbines. So there is a lot of expertise and knowledge about this type of machinery within the ISTEC company. So the importance of vibration measurements on stationary gas turbines, which we want to touch on today. There's also on wing turbines, of course, and a lot of the basics, of course, are the same. So don't jump out of the meeting if you are involved in on-wing turbines. What we see is that the energy landscape is changing significantly, and where turbines initially run mainly on a base load, we see more peak shave modes being used. And peak shave involves a lot of more start-stop cycles, which put more strain on the turbo machinery, and therefore wear and tear are increasing. And hence we see that condition monitoring becomes more and more important to monitor the changes of the behavior, the mechanical health of the turbines, and monitor them in time. So the operator can, on time, start to think about implementing maintenance activities when needed. So let's start with the basics of vibrations. How does it work? And vibrations on gas turbines, on steam turbines, are a lot alike the smaller rotating equipment. So it's good to have a good understanding of the basics of vibration and able to recognize the most common causes. And in addition to the basic vibrations, there are also more complex causes, of course, which could also be specific to gas turbines. And they are very interesting, but because of the time constraints today, we will have to save that for another webinar. But this is a good start. So we can visualize vibration as a mass on a spring. So as you can see here, if we pull the mass downward from the point of rest and then we release it, we will see an up and downward motion in the vertical direction. And if we then plot this motion in time, we will see a sine wave with a top and a bottom. And the distance between the point of rest and the point of release determines the amplitude of the wave motion. So the further we pull it down, the higher the amplitude will get. And assuming that there is no damping, then this motion will repeat itself endlessly. And what we can also see is that it needs a certain time to complete one cycle. And this is what we call the frequency. So what we now can see is that vibrations have a direction, in this case a vertical direction. It has an amplitude, so how big is my vibration? And it has a frequency, so how often in 1 second does the wave go from top to bottom and back. The previous slides, of course, showed a pure sine wave, which is really clean and a good example. But in reality, we all know that there are different excitations in the machinery. So they will all come together in a combined signal. And if we add the two pure sine waves together, then we will get a more complex sine wave. And we can decompose that into individual components with an amplitude, a phase, and a frequency. And this is done by using the fast Fourier transform. And that is a commonly used representation of a vibration signal during the processing and analysis of vibrations. But it's also important to keep in mind that there are limitations in using the fast Fourier transform. But for many causes, vibrations, it's a very important tool because it gives insight into the different components of the signal very easily, and it's very easy to understand. I hope that the previous two slides have given a little bit of an idea on how vibration is built up and how a complex signal can be decomposed into different components. But yeah, this is just the tip of the iceberg when it comes to the art of vibration measurements and analysis. We have summarized a lot of our case studies in our bookazines, which are free to get. So if you don't have it, you can always ask us to send it to you. We also have established our ESTEC Academy, where we more and more start to share also information about vibrations and also speed. For instance, this presentation we also want to upload to our academy. And since the beginning of this year, we have also launched our own ESTEC Vibration Category 1 Plus course, which is a very good course worth taking if you want to get more familiar with the basics of vibrations. And it is definitely worthwhile. So protection versus monitoring. We want to protect our machinery against too high vibrations, but we also want to monitor it. There are two different schemes. And from the history, they are very isolated as well. So when we compare the both protection and monitoring, we can see that protection has a very simple goal: safety. Prevent severe machine damage. Prevent loss of life. Where monitoring has quite a different goal: maintaining availability and reliability of the machine. And that is two completely different goals, but they use the same data. They use it differently. Data usage in a protection system is autonomous. So we define thresholds. When the machine exceeds the thresholds, the levels exceeds it, machine will be shut down, just to prevent that the levels will increase even further and cause severe damage. Where with monitoring, sometimes even the same data is just used for visualization and to understand how does my levels change over time. And the effect of that is very indirect, while protection is a direct effect. When it exceeds it, it's black and white, stop the machine. There are also still requirements on protection systems, while on monitoring it's less important or not even existing. And regulations, one of the known regulations for machine protection is the API 670, which is an American Petroleum Industry standard, which defines a lot about the protection of turbo machinery on vibrations, but also on speed. And it's a very good regulation. It gives a lot of insight if you want to know more about, okay, what do I have to consider when I want to look at my protection scheme? While with monitoring, a lot of ISO standards, the ISO 18436 provides a lot of insight in what condition monitoring and also the training of staff should be considered. As I mentioned, in the past, and a lot of systems had a physical disconnect between the protection and the monitoring side. So if you had a rack-based system with different cards, the condition monitoring and the protection were done on different cards, where the protection cards were completely isolated. So you also prevent that unwanted changes are being made. With the current technology state, we see more and more that both can be embedded in the same hardware while maintaining an isolation. And this makes it more flexible to implement both protection and monitoring in the same space. So now we touched on the basics of vibrations, and we talked about protection versus monitoring. Let's have a look at some causes of vibrations. And one of the most known source of vibrations is unbalance. It's like the tire on your car. When you have been doing off-road work and you have a lot of clay stuck into one side of your rim and you start to speed on the highway, your car will start to shake because the mass distribution of your wheel is not optimal anymore. And that's the definition of unbalance. It's a condition where the axis of center of mass does not align with the center of rotation. And in rotating equipment, this can be due to manufacturing errors, tolerance stacks up, but also contamination during operation. And whereas unbalance itself is not dependent on the rotational speed of the machine, the forces due to the unbalance are. And they can cause damage to the gas turbine itself or its surroundings, because it can be quite a major excitation source. There are three different types of unbalance: static unbalance, couple unbalance, and dynamic unbalance. And the one in this slide is static unbalance. And what we see is a parallel displacement of the axis of mass relative to the axis of rotation, and this causes an in-phase motion on the bearing pedestals. A couple unbalance shows that, as in this animation, is that the vectors are the same in amplitude, but are 180 degrees apart, and the center of mass crosses the center of rotation at the center of gravity. And this type of unbalance creates a rocking motion on the bearing pedestals. And dynamic unbalance, which is most commonly seen, is a combination of both static and couple unbalances. And in this picture, it's really simplified, but you can imagine that when a gas turbine rotor is built up, it consists of discs, it consists of blades, it consists of tie rods. It's a complex build-up. So all these components will have their own unbalance vectors, which will all come together as one unbalance source. The next one is misalignment. So when two or more rotating machineries are connected, we have to make sure that the shafts are aligned properly. When there is a parallel misalignment, the shaft center lines are parallel but not in line. And this can be both in the vertical or the horizontal plane. It's also known as an offset misalignment. And that's different compared to the angular misalignment, where the shafts meet at a point but are not parallel. And again, this can be both in the vertical and in the horizontal axis. And yeah, as you can imagine, the combined misalignment is the most common form of misalignment. And this type of misalignment of source can cause a lot of strain on the bearings, on the couplings. It can excite natural frequencies like unbalance. It can cause strain on surroundings, pipes. So misalignment is a very important cause to keep in mind when a machine is being placed, and aligning the machine is very crucial for a proper operation of the machines. When there is a gearbox involved, then vibrations can also occur here, and this can be when there is a missing gear, when there is damaged gear, when there is an issue with the alignment of the gears. There are a lot of potentials when it comes to gearboxes. For instance, when a gear tooth engagement involves a damaged tooth, the forces, the torque which is being transmitted over the gears will be interrupted, and less force can be transferred, and this will cause vibrations. In the gas turbine business, there are two types of bearings being used. So for on-wing, it's mainly rolling element bearings. In the industry, it's smaller gas turbines but still have roller element bearings, but the bigger they get, they will all be equipped with sleeve bearings. The roller bearing can be damaged in several ways. You can see in the picture that it consists of different components: an inner ring, an outer ring, a cage, and rolling elements. And these components all have their own vibration fingerprint. So they all rotate relatively to each other. So when you know those frequencies and you can monitor them, and you can analyze when there is an issue, and you can even pinpoint to which components is causing what. Sleeve bearings are much simpler in setup, involve less components, and instead of rolling elements, a fluid film is used to reduce the friction and to add damping. But when the oil film is not stable, so it cannot form properly, it can break, and it can result in instabilities. Also, is this type of bearing much more sensitive to external influences on the position of the shaft, because there is no fixture. Like with the roller bearing element, it's all fixed together. So we have an inner ring, we have an outer ring, we have a case, and everything is maintained. While with the shaft, it's the oil film which separates the shafts from the bearing. So these were the four most common vibration sources or causes, but there are much more, and we can make a really long list. But a couple of known causes are resonance, flow turbulence, acoustics, loose parts, and more with the introduction of renewable energy in as a source of energy to the grid. When a gas turbine is connected to the electrical grid, also torsional vibrations are are a potential cause which needs to be kept in mind. So now we know the causes of vibrations. What are the effects of it? And we have to keep in mind that every machine vibrates. This is something you cannot prevent. It's almost like a heartbeat of each machine because it involves moving and rotating parts. So as long as the vibrations are low in amplitude, nothing will happen. But when they can become big, then you can get safety issues. What we discussed about the protection, when it comes too high, machine can fail, causing unsafe situation, and in certain cases even result loss of life, and hence the protection systems, which are solely responsible for shutting down a machine before that can happen. Vibrations can start small, can become bigger, wear and tear, bearing wear out, pipes can start to leak. These can all be results of vibrations when they become bigger and bigger. And that will also result in reduced availability, unscheduled downtime. And unscheduled downtime on itself can also cause problems with the production. So supply issues, semi-finished products, quality issues. So a small thing can have a big impact. Yeah, this picture, it's not a gas turbine, but I think it's quite a dramatic picture, but it shows pretty well what can happen when vibrations become too high. This was on a hydroelectric power plant in Russia in 2009, where vibrations caused the metal fatigue at the bolts holding the valve of one of the turbines. And when the bolts broke loose, the valve became loose, and large amount of high pressure water flowed into the generator room. And unfortunately, 76 people lost their life. And it also caused a chain reaction. So it started with one, and it actually caused a really dramatic failure. So to monitor the health of any rotating equipment, a condition strategy must be determined. So let's have a look at these strategies. And the strategy chosen will also affect the hardware to be used. And that will come next in the webinar. So that you can differentiate between three types of condition monitoring strategies. One is periodic, one is online, and one is remote. And periodic is when a condition monitoring specialist will travel to site periodically. So every quarter, every half a year, every week, whatever is being determined, goes to site with this data collector, collects data, and analyzes it. And it's done on a fixed interval. And when storing this data in a database with this fixed interval, you can start to determine trends. To do this strategy, it's required to have specialist knowledge. And it's you can see that everything which happens in between two scheduled measurements is not well visualized. So therefore, online condition monitoring provides more insight in the machine because you have a permanent monitoring system in place. It will continuously collect the data, and this data will be continuously being processed, and all the key parameters which you want to monitor can be presented in real time. But you can also look back 1 day, 3 days, 5 days, 1 month, whatever you want. And you can start to use that to determine if the machine is start to degrade or not. And that can be used to initiate maintenance or to involve specialists to do an in-depth analysis. Also, triggers are used, thresholds. These are not the same thresholds as the ones used for the protection, but they can be used to alarm the operator that when a certain change happening in the vibration signal, you use that to trigger the alarm so the operator can start to take already actions. The last one is like a online condition monitoring plus, which is the remote condition monitoring. It uses the same hardware, but it adds the possibility to do the analysis remote. So from a remote, a condition monitoring company like ESTEC can periodically check the vibrations, which are measured by the online condition monitoring system, and that can be used to determine trends like with the online condition monitoring, but it doesn't require any disturbance to the organization which is operating the turbine, because this all happens on the site. And it's also can be quicker, because when this happens, the specialist will look at it and can already find some issues which are maybe overlooked by the organization. And what we also see is that there is more and more hunger to data for data-driven decision making. And when it comes to this type of machinery, that kind of data, so vibration data, is key, and it gives a lot of insight in the mechanical health of a gas turbine. And when you add this together with the aerothermal data of the gas turbine, you get an even better picture of how the machine is behaving. And on top of that, add the process data, and you get a really well-defined picture of your machine. But it also becomes complex, and without the experience and knowledge of specialists who can provide context to the data, any attempts to automate things poses a risk of making wrong decisions. So selecting the hardware, the right sensor, the right measurement system is key, because if the data is not proper, you can make wrong decisions very easily. A false sensor can lead to false input signal, which affects the quality and the accuracy of the monitoring, the protection function. So it all starts with selecting the right hardware. And that starts with the sensors. Now, 3 types of vibration sensors. So accelerometers, acceleration sensors, velocity sensors, and displacement sensors. And acceleration sensors are the most commonly used. They have a really broad frequency response. The general purpose go up to about 15 kilohertz, but specialist lab sensors can even go far beyond that. They can measure in single, dual, or triaxial directions, and they are available in a variety of different designs. And an acceleration signal can also be integrated to velocity. Velocity sensors have a much more limited frequency range, so from 1 Hz to 1000 Hz, and they are suitable for vibration monitoring and balancing applications. Because this has a lower sensitivity to vibrations in the higher frequencies than accelerometers, they're also less susceptible to overload, which is an issue which can happen when the wrong accelerometer is being selected for a certain application. So with the velocity sensor, that is less of a risk. The displacement sensors, also known as non-contact proximity probes, they measure the relative movement, the vibration between a shaft and a sleeve bearing or another supporting part. This type of sensor has a frequency range of about up to 1500 hertz and is really good in measuring low amplitudes, which are really typical for sleeve bearing applications. Different compared to the accelerometer and the velocity sensor, a displacement sensor consists of three parts: the probe, the extension cable, and a driver. And together they create a tuned oscillation frequency, which is disturbed by the metal surface of the target. And these three are matched, so they can only be replaced by identical components. Otherwise, the calibration of the whole loop becomes invalid. And that's quite a big difference compared to the accelerometer and the velocity sensor. Accelerometer sensor and velocity sensors are, we also call it casing mounted sensors. They measure the casing vibrations, where the displacement sensor really measures the shaft displacement. So these are used on sleeve bearings applications, where accelerometer velocity sensors are used on rolling element bearings applications, gearboxes, also to add to the displacement sensor, so mounting it on a sleeve bearing pedestal to measure the absolute vibrations of the shaft. So we know now what we have to select as a sensor, but where does my signal go to? And there are different systems, types of systems which can be used. A portable data collector. So when there is our strategy is to periodically measure my vibrations, we can use a portable data collector or a portable multi-channel device, which is temporarily hooked up to the machine. We measure a certain duration, and then the data is being analyzed. Online measurement systems are fixed, so they have their place in the system, and the data is continuously being inputted to the system and processed. The portable multi-channel device is a good first step when there is a critical machinery and it is equipped with a protection system, but it lacks condition monitoring capabilities. Then a portable multi-channel system is a good start to get insight into the machine behavior. But at the end, having it online will add much more insight into the machine. So that is at the end, for a proper defined condition monitoring strategy, an online continuous measurement is the best solution. It will give more data and will give continuous information. Common mistakes. So we have hardware, but there is also a lot of things you need to get your hand around when you want to implement it. And there are some common mistakes which are often being seen, which you can also see as a checklist to do the opposite. So incorrect sensor. A sensor has a lot of different capabilities, which you need to take into account. What is my dynamic range? What is my frequency response to sensor? What kind of bearing am I using? So do I need to use a proximity probe, or do I need to use a casing mounted accelerometer or velocity sensor? What is the temperature where I want to measure? Installation, the location, where do I measure? How is the path, the transfer of vibrations towards my sensor? You want to have it as direct as possible. So you want to measure it as close as possible to the source of your vibration. And you also want to install your sensor properly. Again, if it's in a hot environment, can I route my cable properly? Is the surface where I mount my sensor on, is that perpendicular to my sensor? So I don't put any strain on the casing of the sensor. Calibration or periodically checking of your sensor is very important, because the sensor can become damaged. It can start to deviate, and it's used for protection. It's used for monitoring. So there are big decisions being made based on data coming from that sensor. So you want to make sure that the sensor is providing correct, accurate data. There are a lot of regulations concerning vibration monitoring, condition monitoring, and it's easy to get confused and to do incorrect interpretation of regulations. For instance, the ISO 2816 is a very handy regulation, but you need to make sure that you select the right version, the right chapter to base your limits on, because it makes a differentiation between different types of machine: gas turbines, generators, wind turbines, small equipment, big equipment, things like that, racehip engines. Another common error is misperception of the relevance of vibration monitoring. Like, we have never had any issue. Why should I invest? It's too expensive. And it makes a lot of sense, right? When you never had an issue, but you cannot count on the past when you define your future, because things can go wrong, and you don't want to run to a failure. You want to be on time, prevent a major shutdown. Misinterpretation of data. It's easy to get confused when looking at data. Again, it comes to understanding the whole loop. It comes to understanding the type of machinery you look at. We will show in one of our two cases an example of what can happen when you're not cautious about the whole system setup. So we have two turbine cases. One is about ignoring expert advice, which results in a damage. And this is about an oil pump being driven by a turbine, where in January the vibrations were acceptable, and on the 28th of January the vibrations were 5 times higher. And then the data was analyzed to find the root cause. And the different frequencies and associated levels found during the analysis were an indication of wear and increase in clearances on the gears and the bearings, and additionally misalignment was expected. And because of this fast increase, the customer was notified and recommended to shut down the machine and to have it inspected. And the customer acknowledged the results, but decided to continue, which resulted in the pump failing. And what could be seen when the fractures were inspected, that it was a fatigue failure. And the fatigue failure is this type was commonly there was a common cause, which is misalignment. And this misalignment introduced dynamic force on the shaft, which accelerated the fatigue process. And this could have been prevented when the advice was taken and the machine was stopped and an inspection was done. The next one is garbage in is garbage out. So we talked about sensors, we talked about hardware, and this is a case where the effect of errors can easily result in a wrong conclusion. This was a machine where a low frequent vibration was observed, which could be an indication of flow turbulence. And this could be due to variations in pressure or velocity of the air passing through the fan or the blower. And it's a really, this example in vibration theory, a lot of these, when it comes to flow turbulences, it's an example which looks like this. So you can easily think, oh, there is an issue with my flow. But when it was inspected, it was found that the sensor cable was touching the casing, and that was introducing a grounding issue. And grounding issues, so when a cable gets in contact to the casing and there is a contact between the wires and the casing, you can get ground issues. And they can cause the same kind of pattern of the vibration. And it's a completely different problem to solve. So from this case, we can learn that a simple error in the mounting and routing of a sensor, because as you can see on the picture, it's not the sensor's fault, it's not the cable's fault, it's the routing. The cable is not routed properly, or the connector is too big. During the installation of the sensor, there were some mounting errors, which leaded to this. So we're now at the end of the webinar, and we've covered different aspects of condition monitoring on gas turbines. So the question is for you, like, how can I apply this information? So we put some questions here which you can ask yourself. You can use it as a checklist, and if there's any doubts, or if you're not sure, please reach out, because that's why companies like Istex are there to help you out and sort your problems. So, is there sufficient understanding about vibrations and the effects of it within my organization? Do I have a condition monitoring strategy defined? And if so, does it fit the criticality of my application? Did I select the right type of sensor for my application? Is the routing of my cable well defined and checked against possible noise pickup? And provide my measurement system the right tools to monitoring my application? So just when you have time, look at these questions. I think they are a good start. So this webinar is really basic. It's really a start. It's a tip of the iceberg, but it's definitely worthwhile looking into. So that was the presentation. Thank you.